We're finally ready to learn about data structures. In today's video, I'll be covering the most simple abstract data type that we can implement as a data structure, the stack. So before getting into data structures in my channel, we learned why data structures even exist and how to analyze algorithms, each in its own separate video. If you're new to the channel and to computer science and want to learn about data structures, go ahead and kick off my data structures playlist, which will play those two videos and then this one right after. Otherwise, sit tight and let's continue our journey of learning the data structures together. The first detail I want to address about stacks is that, just like all interfaces, they have some set of functions. There is another interface, the list interface, which subsumes the stack, meaning that we can do everything we can do with the stack with the list. So, a stack is a dumbed down list. So why learn the stack? There are two answers to that. The first one and most important one is that each data structure, no matter what, still brings its own unique set of guarantees to the table. We'll get into more detail about that later using a practical example from the domain of web development. But also practically, since the stack is so simple, it helps us isolate our focus more on how we're going to approach learning data structures in the future than on the actual difficulty of whatever I taught you today instead. Now let's get into a real-world motivating example for stacks. So let's say we work in storage and we're trying to stack boxes together. Intuitively, we know that we should probably pile the boxes on top of each other. And we do that one by one, only adding to the top of the stack. Now, eventually, when we unload our stack of material, we're not going to pull from the bottom, obviously, because everything else on top of it would fall. So the only thing we should do is remove from the top again. This very intuitive concept of adding to the top of the stack and later removing only from the top is often named LIFO, which is an acronym that expands to last in, first out. Now, I'm not a fan of this acronym, and I'm only including it for completeness, because in my experience, I've never obtained any value from knowing it. All it is a summary of the stack. Let's pause for a bit. Because what we just did behind the scenes is define the interface for the abstract data type that is the stack. Now let's formalize the interface of the stack a little bit. We can push items onto the stack, and we pass in the item as some parameter. We're going to be working with numbers, so we're going to treat these parameters as integers for now. Then we can also pop from the stack. And what that does is it removes from the top of the stack and returns to us the item that was at the top of the stack. So we just achieved something very cool here. What we did was define an abstract data type, and we're going to be doing this in the future for all of the abstract data types that we're working with. The cool thing about that is because now we can get to working on a data structure and to actually coding this functionality. I'm also going to add the size function to our interface so that we can always get the size of the stack, but I'm going to talk a little bit more about that later. Another commonality between all data structures that we're going to discuss in the future is that they are all built on some underlying data structure. Because it's the only other data structure we know of so far in my channel, we're going to be using the dynamic array, which is the government name of the Python list. Now we have a base for implementing our own stack. As I've stated before, every data structure is implemented on top of another data structure, and the dynamic array is implemented on top of the relatively static arrays. So with a list, what we can do is add to any point in the list, either at the start, at the middle, or at the end, which is going to be useful for us. The dynamic array brings us to another topic that will show up a lot in data structures, positions of data. The dynamic array uses indices to denote positions of data, so if I wanted the second element in the list, I'd access it by knowing its index. The data structures we cover later on will have positions defined through other means, like through something called nodes, for example, but we'll get to that when the time comes in another video. The takeaway is that when we work with data structures, we have an action as well as a position for the action to take place. For example, if we insert to the end of the list, the implicit position is the end of the list or the length of the list. It's also often the case that we can assume the position based on the action, which is why we don't really think about positions too much with data structures. Because, for example, if I know I'm adding to the end of the list, I know that I'm modifying what's past the last item in the list. So now that we have our interface defined, let's get to the fun part, which is coding the stack. I'm going to be using pseudocode since then you can translate the code into whatever language you want. Let's start off with push. Now, given that we have a dynamic array, really all we need to do if we want to add to the end of the stack is simply add to the end of the stack on the dynamic array that represents our stack. Next, considering we said we're going to have a size function, let's keep track of the amount of items that we've added so far. Now that's literally all we need to do for the push function. Now let's define another function, size, which will access and return the counter that we've been keeping track of every time we add or remove from the list. As you'd expect, pop is also really simple. All we're doing is removing an item from the end of the list and returning its value, and also in our case decrementing the size counter. Pop is also going to have one more step, which is to check if the list is empty, because if it is, we don't want to do anything. We want to alert the user of the stack that the list is actually empty. That's all for our implementation of the stack. Notice that the list that we're working with is actually more useful than what we're creating with it. It can be treated like a stack and more. So again, why do we even need a stack data structure? The answer to that, and something that is common amongst most data structures, is that they have some kind of guarantee of their state. For example, if we give somebody a stack, let them pop off a fraction of the items, and we get the stack back, we can assume that the bottom of the stack is untouched. This is exactly what happens with web browsers. Let's say I'm coding up a web browser, and I'm implementing the back button using a stack, which is how it's done. If I use a list, I could accidentally undo items in the incorrect order. With a stack, I couldn't possibly undo items in the wrong order no matter how hard I screwed up in my experimentation. We've reached a point where we have a well-defined data structure, so now we can actually perform an analysis. Let's analyze size. Now, because we had the foresight to increase the size whenever we've pushed into the stack, and to decrease size whenever we've popped out of the stack, we can simply return the size in constant time by returning that counter that we've been keeping track of. That means the runtime of the size function does not depend on the input, we just return one item, so it's constant time. Now we get to a more interesting analysis, that of the push function. So push has a constant number of actions, there's no loops or anything, and it seems like adding to the end of a list takes constant time, intuitively. However, we actually have to understand how the dynamic array works to say that we know the runtime of this algorithm. And sadly, the worst case runtime for the insert function, even at the end of a list, is O of n. To understand why, we have to take a quick detour and talk about computer memory. So when we create a static, non-dynamic array in computers, what happens is our process reserves a bunch of contiguous space in some random part of the computer's memory. Because we reserve a random place, if we take more space, we might be taking the space randomly reserved by another process. To avoid random programs interfering with each other, what we do is copy the array to a place with more space. But instead of copying just one extra piece of space, we actually double the space, because it helps with our analysis. So in terms of our analysis, that means that there's really two types of inserts. One that simply fill in blank space in constant time, and one that doubles the array before filling in one empty space. So if we're assuming the worst case, well, the worst case is that we're going to be doubling our array every time we insert, so that's why we said that the stack insert takes O of n. But your intuition should be bothering you a little bit right now. There's actually a more advanced analysis we can do on this to prove that our inserts won't really take O of n every time. I mean, take a look at this example we have on screen. It took us inserting 3 items, 3, 2, and 1, to have to double the array to add 3 more empty spaces. I phrase it this way because, in general, it will take us n items to insert before we have to do a doubling of n more spaces. Now this tells us holistically, across n inserts, we do only O of n work if we sum all the work. When we have a situation like this, we can say that the amortized cost of one operation is O of 1. Now technically we did not do an amortized analysis, but I gave you an intuition that looks a lot like amortized analysis. Amortized analysis is a more fine-grained analysis and is sort of a hidden skill in the realm of computer science, as it's not common for computer science courses to teach it from what I've heard. There are 2 kinds of amortized analysis, and I'll eventually discuss each of them in their own video. So now back to our stack. We just took a detour that shows that the amortized cost of our push function is O of 1. Now that still means that the worst case is O of n, but at least we've proven that O of n does not occur often in push. Now the analysis of the pop function is very similar to that of the push function. There are a constant amount of operations, but the removal of a list item from the end of the list has a worst case of O of n with an amortized cost of O of 1. The computer memory logic behind the pop function works in an inverted manner to that of the push function. We cut in half the memory we reserve for a list of size n when we perform n over 2 removals on the list. We're going to call this implementation of the stack the ArrayStack because it's built on top of a dynamic array. Now let's summarize the runtimes again. For push, we have an amortized cost of O of 1. For pop, we have the same. And for the size function, we have a worst case cost of O of 1. So we have a pretty good data structure. And we don't often get data structures that have this kind of runtime. But at the same time, the reason we have this performance is because there isn't really much you can do with a stack. So we are done with the first implementation of our first data structure, class dismissed. But for those that are a little more curious, I have one more concept I want to discuss. And that concept is that interfaces can inherit from each other. What this means is that there's actually a hierarchy of abstract data types. For example, there are collections, which almost every data structure inherits from. A collection is exactly what it seems, an ADT that contains a variable amount of items. That comes with its own interface attributes, like keeping track of number of items or iterating over the items. Now, if we take a look at our stack ADT again, we can remove the size function from its interface and pull it out into the collection interface. This completes our comprehensive analysis of the array stack, which is a data structure for implementing a stack. There are other ways to implement the stack that work better but that require data structures that we have not yet learned. Again, although we digress in our algorithm analysis into computer memory, the key takeaway from this video should be the guidelines we followed in defining a data structure. I'll see you guys all in the next video.